Hello, in this video we're going to look at a quick introduction to statistics. Now if you want the notes for this video, they're in a PDF in the comments below, so you can go ahead and click that and then follow along with this video. So the motivation for our statistics here are the following record high temperatures from the last 21 years in Winnipeg, which is the city where I currently live. So if we look, we had 38 or 35, 33, 34, 36, and so on. These are the record high temperatures, so not with the humidex or anything else, it's just the highest temperature that was recorded all year. Now, what we might want to do is explain to someone what Winnipeg summers feel like using only one number. And you could say to somebody, well, you know, the highs for the last 21 years are the following, but it's a lot of information to give someone. It would be more helpful if you could say, you know, on average, what was the hottest day? Or when coming to Winnipeg, the worst you can expect for the summer, or the best, depending on whether you like it hot, is the following. And it would be nice if that number you gave them, the description of the Winnipeg temperature, was only one number. Well, there are different numbers actually that you could use to describe Winnipeg. One number is called the mean. So the mean, sometimes called the average, is found by adding up all the numbers and then dividing by how many there are. So what we would do is we'd take all of these numbers and we'd add them up, and then we'd divide by 21 because there's 21 of them, and that would give you the mean or the average of the highest temperatures. Now this is sometimes written in statistics with fancy formulas like this. The 1 over n here means that we're going to divide by how many numbers there are, and this formula means addition. It means the summation. We're going to take the summation of all of the xi's. Xi represents each of the temperatures. So this would be x1 over here. This would be our x1. This would be our x2, and then x3, and so on and so forth. So we're adding up. This here means to add up. And so we're going to add up all of them, and then at the end here, this portion allows us to divide. So it's just a fancy formula that says what you hopefully know. To find the average, you add up all the numbers and divide by how many there are. But that's not the only number you could summarize the temperature with. Another number you could use, and hopefully you've learned about this before in mathematics, is the median. The median is the middle number. So what you do is you order the data from smallest to largest, and you cross off one value from either end until you reach the middle. So for this one, we could go ahead and let's say we cross off the 30 and the 38, then the 31 and the 37, and we just continue like this, crossing off until we find the middle. So you keep going, you keep going, you keep going, and looks like there's only one number left. This would be the median, the middle number right here, 34. Now, just to back up, we could also do the mean. We can go ahead and calculate this. If you add up all of these numbers on a calculator, you're going to get 709. That's going to be the total when you add them up, and it's over 21. So if we type that in on a calculator, 709 divided by 21 would be 33.8 if we round it to one decimal place. And notice these are not the same number. The average temperature, or the average highest temperature, was 33.8. And the median was 34. Now they're close to each other, but they're not exactly the same number. That's why we have different number summaries. A final one that you might have heard of is called the mode. The mode is the number that appears most often in the data. So if we look here, it looks like the 32 appears 4 times. The 33, there's 4 of those. So we can look here, there's 4 of the 32s or 4 of the 33s, 3 of the 34s, but look at that. There are 5 of the 35, so the mode would be 35. Now again, that's different from the median of 34, and different from the average, but they're all in the same ballpark. And the range is another number you could say to somebody. This one is taking the highest value and subtracting the lowest value. So we would do 38 minus 30, which gives you 8. And so as a summary, we have the mean of 33.8, the median of 34, the mode of 35, and the range of 8. Now each one of these numbers has strengths and weaknesses. Of course, the most accurate definition, or the most accurate way to convey the information of the temperature in Winnipeg, is just to tell them, rattle off all these numbers. But most people don't want to stick around for all the data. They just want one number summary. So you might say to them, the mean, the average of the highest temperatures was 33.8. Or you might say the median, the middle temperature was 34. You might say the one that happens most often, the one that you feel like you're going to most likely get is 35. Or they might say, the range of the highest to lowest was 8. Each one of these provides some level of information. It's not the full data set, but it gives you at least the gist of what the temperature is like. So each of these numbers is a way of describing a Winnipeg summer to a tourist in just one number. There's another common way of communicating data, which is called the 5-number summary. So here what we're going to do is we're going to provide the minimum value, the maximum value, and the 3 quartiles, the first quartile, second quartile, and third quartile. Now the second quartile is known as the median. So as a diagram here, what it means is you're finding that middle of the data. Q1 and Q3 mean you're finding the middle between the middle and the minimum, or the middle here between the middle and the maximum. So you're dividing your data into 4 equal sets. So it's 25, 25, 25, 25. Let's go ahead and see if we can do that with our data. So we found, of course, the minimum right here. So this is our min. We've got our max over here at 38. We found the middle was 34. Let's just go ahead and do that again. So we could cross here, 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 and so on until we get to our middle data. So this right here is our second quartile. And then what we do is we go ahead and play that same game, but between the middle and the minimum. So over here, let's cross like this. Looks like 32 is the first quartile. And we'll do the same thing over here. .35 is the third quartile. So our 5-number summary is, and sometimes we like to put these in brackets, 30, 32, 34, 35, and 38. And that should give you a pretty reasonable idea of what the summer's like in Winnipeg. It's more than one number, but it combines a few different numbers. 5, which is better than 21. We've got the lowest, the highest, the median, and then the median of the median, the first quartile and the third quartile, or the median between the minimum and the median, and of course the median and the max. So this is called the 5-number summary. Now, perhaps you wanted a visual method. Maybe you didn't want to give people numbers. Sometimes people don't like to be handed numbers. They like to be handed a picture, a diagram. And so one thing we could do would be to create a bar graph. So we would look at each one of these temperatures, and we would create a bar equal to the amount of times that that temperature occurred. So looking at our data, it appears that we have 1 for 30. So we'd make a bar of height 1. For 31, it also occurs 1 time. For 32, it occurs 4 times. For 33, we also have 4 times. For 34, we just have 3 times. For 35, we have 5 times. Remember, that's going to be the mode, the most often. 36, 37, and 38 are each just once. And so a diagram like this, again, is a helpful visualization. We have, again, the summary here. We can see at a glance. It's not necessarily giving you each one of the numbers. And it's saying, okay, well, it looks like this is kind of the cluster. I feel like this is the most likely place I'm going to get my high temperature, between 32 and 35. That feels pretty likely. 38, not quite as likely, and 30, also not quite as likely. Now, another representation is a box and whisker plot. You probably haven't heard of this in your math education so far. But what we do is we take our 5-number summary and we just go ahead and draw it. So we draw the 5 marker lines from our 5 numbers, which, if you recall, are 30, 32, 34, 35, 38. Then what we do is we draw a box from Q1 to Q3. So just like this, creating a box. And then we draw lines out to these two, which are called the whiskers. So it's called a box and then whisker plot. Now, because of the way this box is constructed, this to here is 25% of the data, and this is another 25%. So this box right here contains 50% of the data, and then the other 25% are on either side, out to the whiskers that are at the very edge, right, the maximum and minimum. So again, it gives you an idea, it gives you an intuition, a diagram, a way of communicating data to someone about the temperature in Winnipeg. Now, one thing we might want to know about the data, other than a 5-number summary, is the spread of the data. So let's look at the following numbers for daily temperatures for two hypothetical cities. Let's look at City A and City B. City A is a bunch of 34s, a bunch of 35s, and then some 36s. City B has some low 20s, and then even up into a 50. My goodness, that's a bit of a strange city. Well, do they have the same mean? Let's go ahead and calculate it. Well, if you're careful to add it up for this first one here, you should get 665 over 19, which, if you go ahead and divide that, gives you 35. And if you do the same here, you also get 665 over 19, which gives you 35. So do they have the same mean? Yes. They both have a mean, an average of 35. But are they the same? Do these both feel the same? Well, City A feels like, yeah, I'm going to get 35. That feels reasonable. But I don't know about City B. Intuitively, you can tell that City B, it's very wild and spread out. While the average temperature is a nice 35, it actually only has that temperature on one day. Most of the days, the temperature is all over the place. And so we need a way to measure the spread of the data. Because sure, you got a 35 there, but that doesn't seem like what's going to be happening most of the time. It seems like the data is very spread out all the way up to 50 and all the way down to 20. So we need to figure out a method for this. How could we measure the spread? Now, one of the ways to measure the spread is called the range, and we've already talked about that. So the range for the first one would be 36 minus 34, which is 2. And the range for the second one would be 50 minus 20, or 30. So these two cities definitely have different ranges, and you can see that the data is spread out. But let's find a different measure for spread than just range. One thing we could try to do is find the average difference that each point is from the mean. The average difference. Well, what would that look like? Well, let's go ahead and take the data points. And remember, our mean is 35. So let's look at the difference from the mean. So 20 minus 35, that's going to be negative 15, negative 14, negative 12, negative 9, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, and we keep on going. 5, 9, 12, 14, and 15. So these are the differences from the mean, how far spread out it is from that average of 35. And let's go ahead and add these all up. Let's add up all the differences and see what we get. So I encourage you to pause the video here, try to add up those differences, and see what number you come up with. Well, if you were careful with all of your addition with the negative signs, you should get 0. Which, well, I guess maybe we could take the average of this. So 0 divided by our 19 different measurements, well, that's just going to be 0. Which isn't very helpful for us. That doesn't tell us anything. The spread certainly can't be 0. So we need to do something else here. This clearly isn't working yet. So the problem with this method is that when we add up all the differences, they actually cancel out and we just get 0. So instead of doing that, let's go ahead and square each difference to get a positive number, and then let's average out all these positive numbers. So here we have the differences again, but now we're going to square them. So negative 15 squared is going to become positive 225. Negative 14 squared is going to be 196. Negative 12 squared is 144. And then 81, 25, 16, 9, 4, 1. 0 squared is still 0. And then 1, 4, 9, and so on. So we start doing all these squares. Now notice, they're all going to be positive numbers. And that's very, very important because when we go ahead and add them all up, we're not just going to get a sum of 0 now. So again, I encourage you to pause the video and see what you get for the total sum. So assuming you're careful with your addition, you should get 1,402, which if you turn into an average, we do 1,402 over 19, which gives us 73.8. So this now, again, is a pretty big number, so it's hard to exactly say what this number means, but at least we have something that's not 0. We're getting closer to some understanding, some number that represents the spread of the data. Now, this number that we looked at, this 73.8, actually has a fancy name in mathematics. It's called the variance. And the variance is the sum of the squares of the differences between the data points and the mean. And I know that's a real mouthful, and the formula here looks pretty scary, but all it is exactly the process we just performed. First, we have this inside part, x minus mu. Now, mu is a Greek letter, and it just means the average or the mean. And so, average slash mean. And so what you do is you go ahead and calculate each data point, subtract the mean. Then there's a square, so we go ahead and square it. And again, this just means add. So we add up all of the squares of the differences. Finally, we have 1 over n, and that's where you divide. Remember, at the very end, we had to divide by 19, the number of data points we had to make it an average. And we get this Greek letter here. It looks sort of like a circle with a little line off it, a little tail, and that's the symbol for variance. Now, variance is rarely used on its own because instead the variance, well, it's an important tool to calculate the standard deviation, which is a much more intuitive tool for understanding the data. So the standard deviation often looks like this, which again looks like a scary formula, but all it is the square root of the variance, the square root of that number we just calculated. So in our case, the standard deviation would be the square root of 73.8, which would equal approximately 8.6. Now, just to note, the standard deviation for the other city, city A, you can calculate to be about 2.8, so square root of 8. So if you notice, the second city has a spread or a standard deviation of 8.6. The other one has a spread of about 2.8. Those are very different numbers. A small standard deviation suggests a small spread. A large standard deviation is obviously suggesting a large spread. If all the data had the same value, for example, if the temperature was always 35, then there would be no spread at all and the standard deviation would actually be 0. So we can expect the majority, but certainly not all of the data, to be close to the mean, and the spread tells us how close. In fact, we can expect a large portion of the data to be within 1 standard deviation of the mean, which is to say if we compute the average or the mean, and we add the standard deviation or subtract the standard deviation, we get a range that includes the majority of our data. So in our case, if we did 35 plus 8.6 and 35 minus 8.6, that would give us an approximate range that includes not all the data, certainly not all of it, but a majority of the data. So as numbers, this would be 43.6 and 26.4. So we would expect the majority of the data for those temperatures to be between about 26 degrees and 43 degrees, which again is a significant spread. That's a large temperature fluctuation that you're going to get in this city. And so that tells you something different than, say, city A, where we would expect in this case, because we had a spread of only about, call it 3. 35 plus 3 and 35 minus 3. So this is going to be between 38 and 32. So this city seems to have a large portion of days that are between 32 and 38. Seems like you could always wear shorts and a t-shirt. A very hot but nice weather, very consistent. Over here, you're going to have some days where you're melting at almost 44 degrees, and some days where it's actually getting a little bit chilly in comparison at only 26. So there's a larger spread of temperatures here, a larger range, and that is helped to be explained and helped to be communicated using this tool called the standard deviation. Now, it's important to know these statistical concepts because they arise frequently when reading any kind of scientific literature. So here's a research paper, and we have a data table talking about diabetes. So it says number of subjects, 1,148, mean, bracket SD, age, bracket years. So the 56 is the mean or the average age of the participants, and SD means standard deviation. So they're telling us that the mean age is 56 and the standard deviation is 8. So we can expect the majority of the subjects to be between 48 years old, right? We would do our 56 minus 8, which would give us 48, and 56 plus 8, which gives us 64. So we can expect this to be the range for our subject ages, which means we know the study is not about children. And that's very important when reading a study. You need to know the age of the participants, who's being studied in this medical study, and the data is given to you in terms of the mean and the standard deviation. They're not going to list all 1,148 ages of the subjects. It just takes up too much information, and frankly, there are some privacy concerns with listing all the ages of the people participating. What they're going to list instead is the average age and the standard deviation of those ages. Now, data summary is one important area of statistics, often called descriptive statistics. The other important area is prediction or predictive statistics. There's often a relationship between two variables, for example, hours studied and the grade earned. However, the relationship is not perfectly linear. So it's not like this. The more you study, the higher your grade. Unfortunately, real life doesn't tend to work out as clean as that. What we usually get in real life is something like this that looks kind of linear. It appears that on average, if you study more, you get a higher grade, but sometimes it's maybe up a little bit or down a little bit. It's not entirely linear. It's what we say is kind of linear. And so our goal is to find a linear function that approximates it as accurately as possible. We want to find something that fits the data. So to do so, we're going to find some averages and some standard deviations. We're going to use the tools that we developed in this video. So first, let's look at the hours. So the hours studied, we want to find, well, let's find the average. So to do that, we need to add up all the hours studied. So we add up all of these hours, and we divide by how many there are. Rounding to 2 decimal places, you should get an average of 3.33. Next up, we want to find the average of the grades. So you add up all these grades and divide by how many there are. Rounding to 2 decimal places for the grades average. That will equal 73.27. Now we can go ahead and use that to find the difference from the means. Remember, this is going to be used for making that standard deviation. We look at, for example, the hours. So we look at that 1, and then we look at that 3.3, and we go ahead and subtract. So 1 minus 3.3 is going to be negative 2.33. Or we do 1.2 minus 3.33. So it'll be negative 2.13 and so on. So you fill in the rest of these. And then we go ahead and square those. So that'll give 5.43 or 4.54 and so on as you go down the list. Now we can do the same thing for the grades. We can go ahead and look at the grade of 40 and look at the average of 73.27. We can subtract those, and we're going to get negative 33.27. Or for the next one, for 50, we'll get negative 23.27. You can go ahead and square those. This will give 1106.89. And this will give 541.49. And again, you can go ahead and continue these. Now, the product of the differences, this is a bit of a weird quantity, but just trust me on this, it's going to be important. We take, for example, this negative 2.33 and this negative 33.27, and we multiply those two. So when you multiply those two, you should get 77.52, and this will be important later. But we'll just go ahead and calculate this. The next one would be 49.57, and so on. So you get a table that looks like this. So here we have all the data filled in nice and cleanly. We can go ahead and use these to calculate the averages, because remember, we always calculate the average of the squares, so we might as well calculate the average of these differences that we calculated. So for these squares here, the average will be 2.38. So this is an average. We also could calculate the average of these squares. It'll be 248.33. And the average for the differences will be 23.62. Now, these are the variances of these, and we always want a square root. So now we go ahead and find the standard deviation. So that's that little symbol like this, which is going to be the square root of 2.38. And over here, the square root of 248.33. We're not going to bother square rooting that last number of 23. And so this should give you 1.54 and 15.76. Now, calling both of these the standard deviation starts to look a little confusing because they have the same symbol. And so what we tend to do here is distinguish. We might give this one a little subscript that says maybe hours, because that's the standard deviation for the hours studied, the spread of the amount of hours. And if you look, that seems pretty reasonable. 1.54, that's how much they're spread out approximately. And over here, this might be the standard deviation or the spread for the grades. And you can see that, again, the grades are 15.76. The grades are spread out more than the hours. The highest and lowest hours are 1 and 6, but the highest and lowest grades are 40 and 97. It's a bigger spread there. So we're going to take those, and we're going to now plug all these into some fancy formulas. So our straight line that we're going to need to approximate this data with, we'll need a y-intercept and a slope. Remember, whenever you're making a line, you need a point and a slope. We can hopefully remember our classic y equals mx plus b. So we need to find our y-intercept and our slope. To determine these, we're going to use our knowledge of averages and variances, standard deviations, and calculate everything. So, like we had before, we had our average for the hours, which was 3.33. Our average for the grades, which was 73.27. We had our variances for the hours and the grades, which was 2.38 and 248.33. We had our standard deviations, which was the square root. So the square root of 2.38, or 1.54, and the square root of 248.33, which was 15.76. And like I mentioned, we need one more strange number, and if you're interested where it comes from, you of course should study more statistics. We calculated the product of the differences and found the average. So this was 23.62. So now we're going to use this strange number because it was looking at the numbers and their differences in relation to one another. It actually measures how correlated the data is. It measures how similar the two are going with each other, how similar to a line they are. When you study more, do you get a higher grade? Are those correlated? Do those seem to happen at the same time? And we use the following formula to measure it. We calculate this value R, which is S, which we know to be 23.62, divided by, well, we need to find the standard deviation of hours, so 1.54, 0.54. We times by the standard deviation for the grades, which is 15.76. And you calculate this to be 0.97, and you could add more decimals. Now, this number here is called our R. It measures how correlated the pieces of data are. And this seems to suggest that our data is highly correlated. You'll study this more in other courses, but this number ranges between -1 and 1, depending on whether it's a positive or negative correlation. In this case, it's very close to 1, which means there's a very close positive correlation, which is going to mean, as we look at our data, that, of course, studying more hours indicates better grades. Now, we can also calculate M and B. These come from, again, formulas. So we do 0.9731, I'll use a few more decimal places for this portion, times by our standard deviation for grade, which we look up as 15.76, divide by 1.54, and we get 9.9, let's say 587. For our B value, we go ahead and find the average for the grade, which was 73.27. We subtract M, so subtract 9.9587 times our standard deviation for our hours, which was 3.33. And that gives us 40.1076. So here we have some numbers, and let's try to do this on Desmos. Let's plot the data and see what this all means, what this all looks like. So here we can see Desmos, and we have our data plotted there. We're going to go ahead and type in our equation. So y equals M, which we found was 9.9587, x, plus B was 40.1076. Now, if you look, this seems to be a pretty good line. If you were to try to draw a line that fit the data the best you could, I don't think you could draw a line that would look much better than that. That seems to go through as many points as it can, and it seems to approximate the data quite well. And these numbers now have significance. The 40 here represents the grade that you would expect to earn if you studied, well, 0 hours. And the 9.9 seems to indicate that for every extra hour of studying, you should expect your grade to go up about almost 10%, which seems to be what happens. The people who studied very little seem to score around 40 or 50, and as the people studied more hours, they seemed like approximately every hour of study produced about 10% increase in their grade, which is quite an interesting example and quite interesting to have that data then actually tell you something. This is now predicting things. You can predict your grade based on the amount you've studied. The interesting thing as well is that this is something that Desmos has built in. So let's go ahead and do this again. What we do, though, is we go as follows. We type in y, and then we do subscript 1. So we're going to do a small 1 here, because that represents part of our data. We're going to put this little symbol. We're going to put our M, and we're going to put X with a little 1 to represent the other portion of our data, plus, and we'll put B. Now, if you look at that, it appears that Desmos has automatically made our line for us. The values are slightly different because we rounded in our example. But you can see the B value of about 40 and the M value of 9.9. Desmos knows how to do this whole thing automatically, because what we've just done is called regression. It's a very important area in statistics because it allows you to predict things based on data. It's where you get ideas like if you study 1 more hour, you're expected to get your mark up 10%. Or in the health industry, if you sleep for more than 8 hours, you're expected to reduce your risk of thus and so. All of those types of studies where they tell you if you do this, you're going to have this result are based on examples like this, where they've collected data, they've done some statistical analysis, likely regression, and they've been able to say, well, we are going to predict this is going to happen for you. And so this mathematics underlies a lot of what happens in the media when new scientific studies come out and we're trying to figure out, how does this affect my life? What is the meaning for me? The meaning is often found in these types of mathematics. And so it's important to become literate with this so you can better understand the claims that people are making. Are they true? Are they supported? Are you able to look at the study? Are you able to do some of this mathematics for yourself and see whether or not it actually bears the claim that the authors are making? So hopefully you enjoyed this quick introduction to statistics. And as always, thanks for watching.